Hey, how's it going, guys? Dr. John here for extraktLAB, Extract Talks. We are here once again to continue our series on GMP. We're talking about GMP fundamentals. So with these types of subjects, you're always kind of wondering, do people really listen to these? They're so boring. We're talking about risk assessments and all that stuff, but we're continuing to hear great things from you guys on it, saying, hey, just keep going on with it. And yeah, I think it should be pretty good. Keep going with the series. We're excited about doing more of these. Okay, so here's what we're going to do. We're going to talk about utilities today. Of all the things that we would want to talk about, utilities. I mean, that's really high up on your list.
Very high, very high.
Yeah, it is what you need to know. Okay, so make sure that you enjoy our free resources. We have to put this up because you guys always are kind of, you guys are interested in making sure that you have resources. We are interested in making sure that you have resources. We have product tours. We got mini courses. We got guides. We got calculators. We have talked about this slide pretty much for the last 6 weeks. Talking about the inputs, all the GMP outputs, which would include, the cannabinoids blending up with the excipients, going into formulations, into final dosage forms, and packaging. We've been talking about, all of the different systems that go into that. We've been talking specifically about the Q7. We've been talking about pharmaceutical quality systems, everything related to that. Direct impact systems. We've been talking about critical processes. So if you get a chance, go back and look at some of our stuff. Right now, we are deep into the Q7, going through it. Today, we're going to be talking about is utilities and utilities for process support. This would kind of really address a lot of the things that can get very complicated in a design for your facility. And the reason we're talking about it is oftentimes those utilities have a direct impact on the GMP. In other words, they have to be qualified by your quality unit within your facility. So they also, it turns out, have to be commissioned. Typically, you would go through a design review, and then you do your risk assessment, of course, on those. You then would deliver those systems, and the critical ones that were established to be critical during the process would be designed and be commissioned and then qualified. So some of those would include, say, your compressed air, process air, or your process gases. Maybe it would be your vacuum, inert gas, all your glycol units, process chillers, for example, bulk storage units, electrical distribution boilers, CIP systems, sprinkler fire systems, for example, classification of the rooms. Sometimes the rooms themselves will have an indirect or direct or no impact on the actual product quality. Again, we're always going back to the API, okay? And the API is essentially, does it impact the API or does it not impact the API? Is it indirect impact or is it direct impact? If it's direct impact, then of course we qualify it and we commission it. These are just some examples. You see mechanical seal systems. That's another one. Like, for example, if you have a pump and you have a seal there, does the seal itself have a direct impact on your process? For example, is there a possibility of the process fluid, the mechanical lubricant, for example, leaking into your process? And is that impactful? Okay. In other words, is it a food grade, or is it going to screw up a system that's later on down the stream, is going to impact your quality? Then those are the things that need to be, addressed and controlled. There's different categories. I had mentioned this before for your utilities within a GMP design and within a GMP system. And of course, we can help you with all this stuff. It can get very complicated when you're talking about all of your pressure calcs, all of your tubing, your fittings. How do you really create all your glycol loops? How do you create your boiler systems, and how they impact the actual equipment and the design of the equipment for what its intended use. I'm going to hit on many of the systems, but they're only a fraction of the systems that you need to think about in a total design. So risk assessment is used to categorize each utility on the basis of impact. Like I said, also fire hazard should be in there because it's such a large portion of what people do. They're always dealing with some sort of solvent, and oftentimes that has a huge impact on the utilities side of it. And it may actually have an impact on the GMP side of it, so that's why I put it in there. There's several different categories. There's the direct impact. That's where you have to have the commissioning and qualification, and you also have GEP, which is good engineering practice. No impact. You only have GEP there. Or, any kind of international building codes, any kind of international fire codes, any type of codes and standards are then applied to that. So they're still important. You still have to design them. You still have to have specifications for them, but they wouldn't be qualified specifications from your quality unit, like I said. Same thing with the no impact and then the fire hazard. Fire hazard, you might have a special GEP, things that you need to do like ATEX or CSA or NFPA guidelines that you're applying to your utilities. Like I said, the direct impact has a direct impact. It can influence or change the API. Direct impact systems must be commissioned and qualified. And GEP and special engineering codes still apply to direct impact utilities. DI, or that's not DI water, guys. That's direct impact systems are designed, constructed, commissioned, qualified to specifications. That's where we were talking about user URS or user requirement specifications. Those are the specifications that are in there. If you go through a risk assessment first, then you create your URS, then you commission the materials to be built according to the specifications. Then after they're made, you commission them according to those specifications, and then you qualify them for actual performance after they're made. And the qualification really comes from your, again, quality unit. You really need to think about when you're talking about direct impact systems, specifically the materials of construction. The general rule is that it cannot be additive. There's a big, I don't know if you wouldn't call it a controversy, but I think a lot of people don't understand the difference between 304 and 316 steel. Sometimes they're using a 304 stainless steel if they have an inert gas inside of it, or that has no possibility of any acid halides in it, it has no impact at all. Therefore, you can use 304. But a lot of people, they just like, oh, well, we've always used 316, so 316 is the requirement. You should look at your risk assessment and say, here's a range of materials that are available to the manufacturer or to the pipe fitters or whatever that they can use because there's no impact on it. So we know this firsthand because some of the GMP consultants that we've dealt with have misapplied without any knowledge of the process, without any knowledge of maybe chemistry, basic chemistry. They've applied a certain material standard, like you have to use 316 when it has no impact at all, neither on additive process or any GMP impact or any direct impact at all. It's just what we have to do. And here's your specification. Well, that drives a lot of cost because, okay, yeah, sure, any manufacturer can go ahead and do that. They can do 316 materials or 304 materials, but if they have to change their entire process of the equipment that they currently make, you're going to have to pay for that. So one thing that a end user needs to be very aware of when they hire an engineering firm, just know that they're oftentimes not the process experts, and you need process experts with, some sort of understanding of materials and chemistry so that you can make the best judgment as to the cost. Because it's always easy just to, specify the most expensive thing, and you're really not doing, as an engineer, a service to your end user, to your customer when you do that. It's actually not fair, and it has no basis in reality, even, so keep that in mind. Just a, caveat emptor to those owners who are out there listening to their engineers. You should have a good SME, or, you should have a good, systems expert. We can be that for you. If you give us a call, say, hey, I need a systems expert. I need to review the plans. I need to look at these things, or if you need design plans, that's what we do. You can come call us. We'll help you. We'll help you identify the right codes, which codes are important, which codes are not. And then we become basically working for you. And you'll have a check on our work, basically because you're going to be hiring, mechanical engineers, or you're behind an MEP engineer or whatever, an assistant or something like that, or an architect to really get all that other stuff done. So general system classifications. Here's some examples for you. Here you got inert gas, CO2. Here you got I'm categorizing it as a direct impact because the CO2 comes in, it touches the plant, and all the little oils dissolve within the CO2, right? And then, yes, it will have a direct impact on the quality. And, if you have dirty CO2, for example, coming in, that would be, or like with solvent reuse, for example, if I'm using ethanol and then I reuse it and reuse it and reuse it and reuse it and then don't qualify it, don't follow the rules on validation, don't follow the reuse or the maximum number of time use rules, and just say, oh, I'm doing this because I'm saving all this money. Because if I actually follow the rules, I'd go out of business. Well, that's something that you need to think about, in terms of whether or not it's a direct impact and all that stuff. So typically the process is, and I'll kind of, explain it to you. You do go through this risk assessment process. Does it have a internal or external impact on, cross-contamination, right? And then you classify it on the basis of that. So you can see the inert gas has a direct, it has a GMP impact, and the documentation would typically be commissioning, qualification, and GMP. As you go down the line, I kind of pointed out gave you some examples of maybe some, utilities that would have no impact, like a compressed air going onto your equipment, right? Your compressed air goes onto your equipment. It may have a specification, like it has to be at 80 PSI. It has to, be dry air going in there, and, it can't be, something along those lines. Okay. That doesn't really have an impact because it's just maybe just changing the valves or something like that. So it's no big deal. Those typically follow manufacturer specifications. So, and GEP and codes and whatnot, they're important, but they won't have necessarily any impact. So they don't require commissioning to be done on them. And the good news is it also doesn't have to be require a qualification. Now, the key to profitability is to reduce the critical systems within your operation to the lowest number so that you are qualifying and controlling the lowest number of systems possible. That's why you do a risk assessment. So you do that right up front, and you're like, oh, well, we don't need to do that because there's no risk to product quality. Therefore, you don't have to, qualify it. If you get a gung-ho, a really go-getter quality person, they're going to try to control everything. But if you get a really good quality person, they're going to say, where's your risk assessment? So that's the type of thing that you need to be thinking about. Glycol water chiller. So if you have a chiller, for example, the glycol water, and it's circulating, say at minus 20 degrees, it could be considered to be a indirect, impact. And what I say in part only on the quality system, because if it chills like a process reactor that has to be at minus 20, the temperature control system then becomes the direct quality impact, and you need to qualify the temperature control system, not so much the chiller, and things like that. So you'll see a recurring theme here as I go through these. Considerations of utilities for all level 3 areas. Here's some, we talked a couple weeks ago and last week and the week before last, we talked about the difference between level 1, level 2, level 3 areas. And the level 3 areas are the highest controlled areas. They have all of the, surfaces all specified in there. They have, they typically are highly controlled. They have certain gowning requirements. Typically you'll have material and personnel corridors that feed them from level 2 areas. And really what you're trying to do is you're trying to minimize the impact to product quality when there's an exposure, a direct exposure of the product to the atmosphere. And so interestingly enough, level 2 areas or level 3 areas would also kind of nicely correspond to like a C1, D1 area. So for fire codes, so you can only really get into a C1, D1 area if there is open exposure of the solvent to the atmosphere. Well, if there's open exposure of the solvent to the atmosphere, you automatically have a level 3 area. So keep that in mind. Piping utilities should be located outside of the area. That's just to make sure that you don't have excess number of people coming in there for maintenance. You don't want to have piping hanging from the ceiling or coming across the ceiling because that has, it has a horizontal place where dust can accumulate. Those are the type of design considerations that you need to be thinking of. And you just want to have those maintenance areas also located outside of the level 3 areas. So those are just some concerns. Now I'm going to go through some examples of some of the utilities, kind of go through some of the thought process and some of the thinking around how you would specify these. And it all goes back to a single common denominator, and that is risk assessment, commissioning, and qualification. So again, process air and gases consideration, for example, specifications are critical. So again, you would have a specification for a direct impact system. Suppose you were blanketing your reactor with argon, for example, to displace oxygen. Well, you'd want to make sure that that argon was non-additive. It didn't add in, say, a process gas that you got from the tank. Okay, you'd want to have a specification for that. You may institute, filtering, for example. You may, if you have process air that is being used to blow out like a filter apparatus, for example, and that filter apparatus then is collected, all the stuff is collected out of the filter apparatus. Well, in that case, you would want the air dried to a specification so it wasn't adding water to your process, right? Because it's a wet air or whatever. So those are the types of things that you need to be thinking about. In general, you're going to be using stainless steel tubing to move your gases around. Copper may be okay. Copper is used all over the world. In fact, for process, like compressed air and stuff. If it is a non-impact, process air that you're using, you just like compressed air for something that doesn't have anything to do with the product, then yeah, by all means you use copper. It's less expensive. But everything else is typically done with stainless steel. You're going to want to make sure that all your seals and all your valves and everything are also non-additive. So don't use bubble gum for your seals. Need to consider maintenance. The lowest point in the system for drainage. Make sure you have points of drainage. Those are the types of things. And you also need to consider the insulation. A lot of people do not consider insulation. And then it's not just any old kind of insulation. You need to make sure that the insulation itself is, cleanable. So that's something you need to think about. Cryogenics and solvents. Here's another example of another system you need to be thinking about. Typically, you do a risk assessment to address cross-contamination. You would address like bulk tank in inspections, the cleanliness of the bulk tank, when it brought in, what the specifications are, what pumps you're using, making sure the pumps are not adding anything with their process fluids. Materials are stainless steel. Engineering polymers for contact materials. Again, we're using stainless steel and engineering polymers. Engineering polymers, I'll give you an example, like PTFE would be one. PEEK would be another, polyether ether ketone. PE, polyethylene, high density HDPE would be another example. Something that is polymerized without the use of a vulcanizing agent or process oils to make it happen. So those would be some examples of some process. FEP, which would be fluoroethylene. Okay, so then let's see. Solvent must meet quality specifications before being used. Okay, this is where a lot of U.S. operators fall down. They want to do things on the cheap. They don't want to follow the rules, and so they reuse their solvents forever. They don't have maximum times that they're reusing it. They don't have a validated method for reuse. A lot of the companies that are doing that right now in the EU and in Canada, if they do batches, they're really talking about throwing away tremendous amounts of ethanol solvents, which is also a huge impact on the environment. Whether it's VOC or whether it's just costly incineration of the product. Okay, so for those people who follow the GMP rules, they're not using ethanol, I don't think, because it's too expensive. So anyway. Maximum number of times a solvent can be reused must be established according to the rules, and solvent must be brought back to its original state. Again, this goes back to cross-contamination, how big your batch size is. So if you have a batch size that's, 180 million pounds, okay, you could ostensibly, I guess you couldn't ostensibly, use it forever because it would continuously evaporate and you'd have to keep on adding to it. But your ethanol, as you use it, would get more and more janky. It would get pretty nasty. So, you're going to have to change that oil out every now and then, boy. So that's how that goes. So, okay. Process vacuum, need venting, need condensers, need insulation. Typically materials is distributed. This is something, process vacuum is kind of interesting. typically if you have multiple process vacuum, you want to have like a big pipe so that's not restricted, because vacuum can be really restricted. Okay, those are expensive. If you're doing stainless steel, think about how you're going to distribute your vacuum. And you can also say, okay, look, well, maybe I'll use a copper pipe that's not so expensive, and I'll make sure that the vacuum, there's no impact on the product quality via that copper pipe. That I've seen that before. Also, you need to think about the proper seals, using KF valves. And I've seen a lot of people try to use like sanitary valves and sanitary fittings for vacuum. Mm-hmm. It's not, it works. It does work, but it's not very good. You should be using the KF if you can. And again, it could be considered to be a direct impact system if your risk assessment showed that there was cross-contamination. Now, vacuum is kind of a big issue because oftentimes, solvents get entrained in the vacuum. They are basically swept and or they diffuse through the system, and then they deposit on the pipes and things like that. And so I like to have dedicated vacuum systems as much as possible. If you have a multi-use facility, in other words, you're doing multiple types of API out of your facility, you should really think about, having dedicated process vacuum. And another thing you need to think about is your CIP system, maybe for your process vacuum lines. So that's just some ideas. Glycol boiler loops. Here's an example of something that typically is not, when I say loops, I mean like glycol piping, chilling piping, piping for process heating or something like that. They don't generally contact the API. One thing that you should do in your risk assessment, however, is you should address whether or not there's a probability of leaks. If there's a high probability of leaks, that glycol could get out and get near your product. If it's in a level 3 area and you have open glycol and you have your product, you could have contamination that way. You typically don't want to have glycol in your end product. Okay. Maintenance should address inspection, heat transfer media specifications so that it can be, can be inspected, and, maybe you need to add glycol over time or something like that. So you got to make sure that it's the same, and then CIP systems, those would be clean in place, or COP, clean out of place systems. There's also steam systems, for example. So these can be direct impact mostly because they're cleaning out the inside of the pipes. And if you use like detergents and stuff like that, obviously you have detergent residuals. Everybody knows about residuals because they can smell their laundry, right? I mean, you can say, oh, okay, I washed my shirt last night and it smells really good. Okay, that's a residual. The residual is on your clothes, and your freshly laundered clothes is smelling really good. Okay. So that's a residual. That's not what's really desirable inside of a pipe that's going to, for example, be feeding the API.
Right.
Or if you were in a food facility, boy, that tastes like Tide. It's that Tide taste I've all grown up to love. Or something like that. I don't know. Let me see here. So anyway, you wouldn't want to do that. So, let's see. Unless you were fond of Tide Pods. Yeah. Oh, that's bad. Okay.
Yeah, I thought that immediately.
Okay. So let me see here. Sampling of CIP stream for qualification monitoring. So probably one thing you need to think about when you're designing your system is that you need to have sampling streams. So you can qualify. People put everything together and then there's no way to get at it without taking it apart. Mm-hmm. So oftentimes, sometimes you got to make sure that you have that in there. It should be in your URS. Okay. Like you have to have accessibility to the system. It's like, oh, well, you didn't put that in the URS. Oh, shoot. We didn't know that. Now we have to cut into it and we have to redo it. That's what happens a lot of times just because it's not convenient. Things you learn in practice, right? Okay. It's the little things. Okay. Vents, this is where you can get in trouble with venting. Okay. Venting of solvents and things like that. First of all, you'd have to dilute it. You can't, there are rules for VOCs and what you vent. Mm-hmm. So dilution's the solution to pollution, right? That's what they say. Well, if you're, for example, running butane and propane and you have a room specifically dedicated to outgassing, all of that's going into the atmosphere and creating, it's ozone forming. Okay. It's so a smog forming is what I should say, because that's what ozone is smog. So, a lot of people wonder why there's a lot of smog over LA. Well, I think you got somewhat of a thing. There's a lot of butane extraction going on there. There's all kinds of VOCs that are being outgassed there, and it's not a little amount. It's like a lot. So you have particulate matter, obviously, that's fog, smog forming. But you also have these VOCs that are also smog forming. Some of the VOCs that are out there also are HAP, which are hazardous air pollutants. You can go on to, onto the EPA site, and you can find out which ones are HAP and which ones are not HAP. Obviously CO2 is probably a really awesome. It's nice and clean. Typically, you would have some aromas. If you condense your aromas before emitting your CO2, it's going to be better for you. You're not going to have like the smell and the aroma from the plant going out and contributing to VOC in your humidity and in your area. So it's important that you think about those things, like how am I going to condense the flavors and aromas out of my CO2 waste stream, for example. Now, CO2 is not, it doesn't produce smog. So that's the difference between the two. That's the main difference between ethanol and butane. So those of you guys are doing, large scale productions of those, even small scale, it's kind of like death by 1,000 cuts on the environment. Thanks a lot, guys. Okay. Waste handling. Dedicated waste handling is acceptable. Common waste streams, piping, may be subjected to backflow. That's something that you really don't think about if you have a waste stream. Okay. So, it's pretty simple though. You just add in you think about it, and then you add in some, backflow arresters, what they call check valves, something along those lines. So it's important. I mean, that's like in a drain, you might have a U shaped in the drain, right? That's what that is. I mean, it's basically preventing backflow of like, sewer gases or something like that. So those are things you need to think about. Now, if you have common waste streams, if they're all coming together, that's another thing, another added level of risk, simply because if there is backflow, even if it's by accident, say something happens and pressure goes up in one area and it pushes the waste from one stream into another stream, well, then you have cross-contamination. You won't even know it. Okay, so those are the types of things that you need to be thinking about with your waste stream and your waste handling. It's better to have, in my view, dedicated waste streams, especially if they're piped in liquid. If they're gas, you may have to do direct vent. But you better make sure that those are always always have positive pressure or are valved so that they can't backflow through. Like if you're venting 4 different solvents into one plenum, air plenum, and then they just vent without any kind of pressure on them, and they intermittent pressure, for example. Well, one of the process gases is going to go into the other one and find the lowest. It's going to back diffuse even, or maybe even backflow into your process. Right. You got to think about that. Okay, so those are the types of things you need to be thinking about. Your risk assessment should obviously really consider that. So just to wrap up here, I'd like to just give you an example of a direct impact system and just kind of do a process here. Very simple. Okay, I have a stirred reactor. I have glycol coming in and glycol coming out. Over here, there's a beautiful, chiller. There's a heater. There's a valve here that kind of changes from the heater to the chiller, or maybe it's a chiller heater. I don't know. And then it comes into here. You got your product that's being made in here. You can see there's a little stir here in your mind's eye. You can see it even though it's not there. And then you can see it's coming. This is the glycol coming out and returning to the process. Okay. And so here's the little recipe I made up. The temperature is ramped to 90 degrees C. It's stirred for 10 minutes at 90 degrees C, then cooled to -20, and then held at -20. Okay, so that's what's happening in here. Mm-hmm. You can see in this case, the temperature control system is deemed critical by my risk analysis because I have to hit those temperatures. The temperature control system itself would undergo a commissioning, and it would also undergo a qualification. It could, because it would be a direct impact specific to the quality and the criticality of the system. The central chiller and the heater are indirect. So the actual systems themselves are actually indirect impact. You would just install those according to normal general good engineering practices and customer specifications or manufacturer specifications. Mm-hmm. But you would really be qualifying just the control system in this case. The jacketed mixer you would want, and the RPM control. Okay, even though I didn't say that the stirring was critical. Our stirring, it is stirred for 10 minutes. Does that mean like it's stirred with a rod, or does that mean is there a certain level of agitation or whatever? So whatever my specification is there in terms of stirring, I would want to make sure that my RPM control is right. Am I going to stir it at 1,000 RPM, or are you going to stir it at 1 RPM? Okay, something like that. Okay, so you want to make sure that it's that at least you're qualifying it so that it's the same every time. And then the jacketed mixer, you want to make sure that that's qualified too. Is it made of the right materials? Is it non-additive to the process? Is there a CIP system associated with that? Right, that would be separate qualification. So that's how I would think about direct and indirect impact systems. And so that's just a kind of a wrap up on the whole idea of utilities. We could literally talk all day about the mind-numbing details associated with designing those systems. Usually your engineers will take they'll do the design, and then they will specify on the drawings all the different requirements, and then those will go through a design review, and then they'll go through a risk review, and then they'll be made, and so and then they'll be qualified and commissioned and qualified. So that's basically your utilities. So hope that was helpful to you guys. When you guys are getting into the process of, defining these systems for your operation, make sure you get a hold of us. We have a lot of experience as a subject matter expert for any kind of botanical processing. And it's not just hemp leaves. We do all kinds of different processing here for different botanicals, and other items that are not even botanicals. So, make sure that you give us a buzz, and maybe we can do a design for you. So, all right. Thanks a lot, guys, and thanks for joining us. Make sure that you look at our beautiful resources page, and maybe revisit our GMP podcast that we had in the past. So, all right. Thanks. Take care. Bye.